Okay, please enter your attendance now in the chat box. Hmm. Hmm. Let's start. All right. Today, we will quickly go through this curl of a vector field in orthogonal curvilinear coordinate system, and then we will discuss cylindrical coordinate system, and probably we can discuss this spherical coordinate system next week, so that we can complete this vector analysis part, and then for your cat 2 we can go for tensor after your cat 1. If we can finish the syllabus early, then that is better. That'll be good. Now, today we are going to study this curl of a curve vector in orthogonal curvilinear coordinates. Curvilinear, this should be I here. So, yeah, typing mistake here and there. So we can consider a vector field something like this, like we discussed in a divergence. This is a vector field in the orthogonal curvilinear coordinate system. Orthogonal curvilinear coordinate system, we have discussed that you are E1 and E2 dot they are 0, or E2 dot E3 they are 0, or E3 dot E1 they are 0. So the tangential unit vectors are at 90-degree. The product between them is 0. That means the coordinate line, the coordinate curves corresponding to the coordinate variable u1, u2, u3, they intersect each other at 90-degree. That is what we mean by orthogonal curvilinear coordinate system. So again, just to recapture what we have discussed before, in this system, curvilinear system, instead of considering our xyz coordinate system, instead of xyz, we are considering xyz are Cartesian coordinate variables. So x exists, y exists, they are x coordinate lines, or y coordinate lines, they are straight lines. But in curvilinear coordinates, we are considering certain coordinate variables like u1, u2, u3, and the coordinate lines may not necessarily be a straight line. It could be a curve coordinate line like this, curve coordinate line like this. But when the intersection of this coordinate lines, when the coordinate lines intersect at 90-degree, then the curvilinear coordinate system is orthogonal system. So that's what we have discussed, right? And we have discussed the transformation relations, tangential unit vectors, perpendicular unit vectors, and gradient divergence. Now we are coming to this curvilinear curl of a vector field. Okay, so similar to the vector field in the case of 3D Cartesian system, where we write A as A1 I cap, A2 J cap plus A3 K cap. Here we write E1 cap in place of our unit vector in the Cartesian system like I cap. Here we have E2 cap, tangential unit vectors E3 cap. Now, in order to take a call in normal 3D Cartesian system also, we have to take a call operation on each and every vector A1i, A2i, like that. So we are following that. Now, gradient U1. This, if you remember this, we have proved it before. Here, I think, where is that? Yeah, here. Grad U1, if we take grad U1, del operator, this is a del operator. This is your del operator in curvilinear coordinate system. orthogonal curvilinear coordinate system, orthogonal curves coordinate system. This is your del operator. So if you are using this del operator operating on u1, and this is what we get: u1 cap unit vector upon tangential unit vector upon h1. H1 is the scale factor, and similarly this and this, that we have seen that before. So we'll just use that property: grad of u1, grad of u2, grad of u3 will be this. Now if you take curl of this thing, curl of instead of e1, from here you can write e1 cap as h1 into grad u1. So this is in place of u1 cap, you can write h1 into grad u1. So this will be like curl of scalar quantity. H1 is scale factor, that is scalar. A1 is a function of A1 will be function of u1, u2, u3 in curve coordinate system. In Cartesian system, you remember that A1 is written as a function of xyz, right? The coordinate variables of xyz. But in the curve coordinate system, A1 is function of coordinate variables in orthogonal curvilinear coordinate system, that is u1, u2, and u3. So A1 is also scalar, H1 is also scalar. So these two together will form this scalar phi. And grad u1, this is a vector quantity. As you see, grad u1 is a vector quantity. It's having vector u1 cap direction. So grad u1, you consider it as a b vector here. So this is a vector identity, which in the last class I have asked you to prove. So this vector identity, using this vector identity, grad of curl of a product of scalar and vector. Curl of a product of a scalar and vector is equal to grad of the scalar cross product with the vector plus this scalar into curl of your vector b. So this del operator, it's just this curl of b. So this is a vector identity which you can prove easily. If you are wondering how to prove it, it's quite simple. Just in case if you are wondering this kind of thing, curl of phi b, right? So this kind of thing you can easily prove. Where is the blank sheet? Yeah, I have a blank sheet here. So this is one vector identity which you have to prove. Something like this. So if you take phi as certain function, phi as a function of x, y, z, let us prove it in the 3D Cartesian system. Okay, so and b vector as b1, which can be a function of x, y, z, I cap, plus b2 is also a function of x, y, z, j cap, plus b3 k cap. So if you do that here, if you just take a curl operator, this will be what is phi b? Phi b vector is equal to, you just multiply phi everywhere here, phi b1i plus phi b2j plus phi b3j b3k cap. So this will be I j k, and del operator means del upon del x, del upon del y, del upon del z, and the first term here is in the phi b is phi b1, phi b2, phi b3. So if you take this cross product, this will result in I coefficient as del phi b3 upon del y minus del phi b2 upon del z. This will be the I coefficient, and the j coefficient also you calculate, the k coefficient also you calculate. I think you can continue. So follow this line. You should be able to do it. Where are we? Yeah. No, I think I've. Yes, we are at this page. So if you use this vector identity, a1 h1 is some scalar, grad u1 is some vector b. So you follow that, it will result in gradient of scalar a1 h1 cross product with b. The vector b is grad of u1 cross product with grad of u1 plus scalar. So the scalar phi is a1 h1 and curl of the vector, this B, right? So this will represent B and this will represent your phi. So like that, if you follow that. So we also know that curl of a gradient of any scalar quantity is 0. So curl of gradient of scalar quantity U1 is also 0, right? And then what remains here is the first term here only. In the first term, you have gradient of A1 H1 cross product with grad of U1. Grad of U1 is already known to us, U1 cap upon H1. So you just put U1 cap upon H1 in place of grad of U1. And there is a cross product here. So what is gradient of A1 H1? You have to write gradient of A1 H1 using your del operator in orthogonal curvilinear coordinate system. Del operator is E1 H1. This is the formula which you have to remember. E2 H2 del upon del U2 plus E3 cap H3 del upon del U3. So this is your del operator in orthogonal curvilinear coordinate system. So if del operator is operating on scalar A1 H1, so this operating on scalar A1 H1 means you have to multiply A1 H1 here, you have to put A1 H1 here, A1 H1 here. So this is exactly what is being done here. So there's a cross product with U1 H1 cap. We know that these are orthogonal system. In orthogonal system, the cross product between identical, this will be magnitude of U1, magnitude of U1, sine of the angle between them. So if you are taking cross product with the same vector itself, sine of the angle between them will be 90 degrees, sine 90 is 0. So U1 cross U1 is 0. But if you take E2 cross E1, so just similar to that, I cap, J cap is K, something like that. J cap, I cap is minus of K cap. So if you just follow the cross product between unit vectors here, in this tangential unit vectors here, similar to what you already know in a Cartesian system, J cross I is K minus of K, I cross J is plus of K, like that. So if you follow that, E2 cross E1 cap will be minus of E3 cap. E3 cross E3 cap cross E1 cap will be E2 cap. So here, this first term E1 cross E1 is 0. E2 cross E1 is minus of E3. E3 cross E1 is plus of E2. So this is what you're going to get out of this, right? So once you obtain this, you can obtain this. You can do the similar calculation. Please do this. Please work out the steps for this calculation. Okay. So curl of A1 E1. What is wrong? Yeah. Curl of A1 A1 E1 cap is this. So similar to this, you can find out curl of A2 E2, curl of A3 E3. Just follow the same step. And if you combine all of this, this is what you're going to get in the case of curl of A. Okay. And this will give you the curl of a vector field in orthogonal curvilinear coordinate system. Now let us see one orthogonal curvilinear coordinate system, which is cylindrical coordinate system. Okay, cylindrical coordinate system. Here in cylindrical coordinate system, instead of using x, y, z as in the case of 3D Cartesian, we are going to use coordinate variables as rho, rho, phi, and z. So these are the coordinate variables. So in cylindrical coordinate system, our u1, one of the coordinate variable, u1 will stand for rho, and our other coordinate variable u2 will stand for phi, and our third coordinate variable u3 is z. So this is what the coordinate variables are in the case of cylindrical coordinate system. Now we will see here what is rho. Rho is actually the distance of any point on the xy plane, the distance of any point on the xy plane from the z-axis. The distance of any point from the z-axis is given by rho. Okay, rho gives the distance of the point under consideration from the z-axis. What is z? Z is simply the height. So for example, if we are going to identify this point here, suppose if you look at this point, there's a point P in this space, three-dimensional space. Using 3D Cartesian system like your x, y, z system here, using your x, y, and z system here, you can identify the location of the point. If you drop a perpendicular from this point on the xy plane, drop a perpendicular from this point on the xy plane, and you are arriving at this point. After arriving at this point, if you drop a perpendicular on the x-axis, then you get what is called the x variable here, the x coordinate value, the x coordinate value. And from this point, if you drop a perpendicular on the y-axis, then you will arrive at what is called the y coordinate value. And if you measure the, if you drop from this point, if you drop a perpendicular on the z-axis, and if you measure this value, this will give you your z coordinate value. Okay, so the location of this point P can be identified using this three-dimensional Cartesian system, x, y, z system. From this point, if you drop a perpendicular on the xy plane, you arrive at this point, and from this point again, if you drop a perpendicular on the x-axis, then this will give your x variable value. From this point, when you drop at the perpendicular on the y-axis, this will give you your y variable value. And this point, if you drop perpendicular on the z-axis, this will give you your z variable value. So once x, y, z variable values are known, then this point is identified. This point is specified. Okay, you are able to locate this point P here in the 3D space. Now, in this three-dimensional space, instead of using your x, y, z coordinate variables, we can instead use rho, phi, and z coordinate variables. So what is rho? So from this point, if you drop a perpendicular on the xy plane, if you measure the distance of this point on the xy plane from the origin, then that distance is called your rho, the coordinate variable. And the angle subtended by this line on the xy plane with respect to x-axis is called your phi variable, and the height here is called your z variable. So once rho, phi, and z are known to us, if you know the value of rho, the distance from the z-axis, if you know the angle subtended phi here, and if you know the height from the xy plane, then you can identify the location of this point. So that approach, that coordinate system approach, that means rather than using x, y, z, we are now using rho, phi, z. This approach of representing a point in a three-dimensional space using rho, phi, z coordinate variables is known as cylindrical coordinate system. Okay, cylindrical coordinate system. So here I'm going to categorize this cylindrical coordinate system as an orthogonal curvilinear coordinate system. We will see that how it becomes an orthogonal curvilinear coordinate system. All right. Now let us, in order to understand whether it's a curve system or not, we have to see what are the coordinate lines. Okay, and we also have to see what are the coordinate surfaces. Right, now rho, what is the rho coordinate lines? Rho coordinate lines is the distance of the point you measure from the origin. So if you increase rho value, it will go like this, considering that all the other values like phi and all the other variables like phi and z are fixed. If you fix phi and z, and if you vary rho only, you start from 0 and you move along this line, it will be a straight line. rho will be a straight line. If you fix the value of phi and z, phi value is fixed, just vary your rho. If z value is also fixed, it will move along this line and will be a straight line radially outward from the origin. Rho is a straight line. Rho coordinate variable or coordinate line is a straight line. Now, what is phi? So if you fix rho and if you fix z, so fixing rho means you are at this point, you are at this point. If you fix z means, let's say z equal to 0, right? You are at this point. Now, if you verify, if you are at this point, phi value is 0 at this point. But if you increase phi value from 0 to 45 degree, you will arrive at this point. And if you increase phi value to 90 degree, you will arrive at this point. If you increase up to 180 degree, you will arrive at the back side here. If you increase up to 360 degree, you will return back to this point. So I hope you can picture here that once you fix rho and z value and vary phi value only, you will move from this point to this point and this point, and you will arrive at this point, and then when phi value increases up to 360, you will again arrive at the original point. Okay, so that means as you verify, you will trace out a circle here. You will trace out a circle here. So there you can see that the phi coordinate line, is now a curved line, or in fact, it's a circle. Phi coordinate line is now a curved line, or in fact, it's a circle. So it's no longer a straight line, as in the case of Cartesian system. In the case of Cartesian system, you can see here that if you increase x value, you will start from this to plus infinity. You can go up to minus infinity along this line. And if you increase y value, you can go up to plus infinity, you can go up to minus infinity. Z value also in the 3D Cartesian system, you can go between minus infinity to plus infinity, but they are always a straight line, right? Now, Z here, Z coordinate variable, if you fix rho and if you fix phi, then let's say you are at this point. If you vary Z from minus infinity to plus infinity, you will go from minus infinity to plus infinity, a straight line. So Z coordinate line is a straight line again. Okay. So because of the fact that one of the coordinate line is a curved line, it's a circle, you can categorize this as a curvilinear coordinate system. Now, what are the coordinate surfaces like? Can you imagine what will be rho equal to C1 surface? See, earlier we just used this U1 equal to C1 surface. So this is the surface that we consider in the case of curvilinear coordinate system, U1 equal to C1. So in this system, instead of U1, we are now having rho. Instead of U2, we are now having phi. Instead of U3, we are now having Z, right? So rho equal to C1. So what will be the kind of surface here if you fix the value of rho and vary phi between 0 to 0 to 2 pi and 0 to 2 pi, and vary Z between minus infinity to plus infinity. If you vary Z between minus infinity to plus infinity, vary phi between 0 to 2 pi, fix the value of rho. What kind of surface we are going to expect here? If you can picture, vary Z between minus infinity to plus infinity means Z value can go from minus infinity to plus infinity along this line. And phi varying between 0 to 2 pi means if you vary phi between 0 to 2 pi, it will trace out a circle. You trace out a circle. So if you fix the value of rho here at this point, if you fix the value of rho and vary phi from 0 to 2 pi, you will trace out a circle. And if you vary Z from minus infinity to plus infinity, this circle will extend from minus infinity. This circle will extend from minus infinity to, just a minute. This circle will extend from minus infinity to plus infinity. So under this condition, if you fix the value of rho, you will obtain what is called infinite cylinder here, like something like this. If you if you vary phi from 0 to 2 pi, start with this point. 0 to 2 pi means you are increasing rho value, and 2 pi you will trace out a circle. If you vary z between minus infinity to plus infinity, you will extend this circle up to minus infinity, and you will extend this circle up to plus infinity. So you will trace out an infinite cylinder. Infinite cylinder, which is coaxial with z-axis. Infinite cylinder which is coaxial with z-axis. See, z-axis is at the axis of this infinite cylinder, right? And that is when you fix the value of rho. Rho value is fixed. So when you fix the value of rho equal to C1 coordinate surface. Rho equal to C1 coordinate surface. Rho equal to C1 coordinate surface, as you see, it's a curved surface, cylindrical surface. Okay, it's a curved cylindrical surface extending from minus infinity to plus infinity, that is infinite cylinder. Okay, rho equal to C1 surface. So there you see that in this coordinate system, rho, phi, z coordinate system, rho equal to C1 surface is no longer a flat surface, it's a curved surface. Now, yeah, let's fix the value of phi. Phi equal to C2. So something like writing U2 equal to C2 surface. Well, you can vary rho from 0 to infinity, because rho is simply a measure of the distance of the point from the origin, right? So rho can vary from 0 to infinity. And your z value can go from minus infinity to plus infinity. Z value can go from minus infinity to plus infinity. Now we fix the value of phi. Let's see what kind of surface we are going to expect here. Let's say this is set. Okay. So let's say we fix the value of phi here. Phi value is fixed at, let's say, 45 degree. 45 degree. Phi value is constant, 45 degree. Let's say your phi value is 45 degree. C2 is 45 degree. Okay. Phi value is fixed, and rho value extends from 0 to infinity, means rho is 0 here. It starts from this to infinity, so it will extend up to infinity. And z value can go from minus infinity to plus infinity. So if you extend from minus infinity to plus infinity z value, you will have something like this. Oops. This control will have something like this. This will extend up to infinity. Okay, you will have flat surface. You will have flat surface touching the z-axis. This is the z-axis. One side of the flat surface is on the z-axis, but the other side is extending up to infinity, because rho value can go from 0 to infinity here. Flat, perfectly flat surface. One edge is along the z-axis, and another side does not have any edge. It extends up to infinity, and the flat surface extends from minus infinity to plus infinity along the z-axis. Okay, so it's a perfectly flat surface. Now, oops, I need one more blank surface. Blank. Just a minute. We need one more blank. Blank, high blank. I just have to create one blank page. Now let us consider another constant, like another coordinate surface. z equal to c3, or earlier we have written this as u3 equal to c3, right? ut equal to c3 as a coordinate surface. Now you fix the value of z. So let's say we have something like this, x, y, z. So let's say we fix the value of z here. Z value is fixed here. Let's say this is 5. Z value is 5. Okay, you need 5. Now, if you extend from here, if you extend 5 from 0 to 2 pi, 0 to 2 pi, you can go around the circle, right? But if you increase rho from 0 to infinity, rho is 0 over here. Now if you draw a line along this line up to infinity, and this infinitely long line, rho equal to 0 to infinity, infinitely long line, if you rotate from this infinitely long line, if you rotate around this from 0 to 2 pi, what you're going to get is, you will get an infinite plane. An infinite plane. Okay, you will get an infinite plane, perfectly plane. This is z equal to c3 surface. So z equal to c3 is a coordinate surface which is perfectly flat, which cuts the z-axis at 90°, and you have one coordinate surface phi equal to c2 surface, which is also infinite plane. One side of this surface is touching the z-axis, and another surface is rho equal to c1. Rho equal to c1 surface is an infinite cylinder. It's a curved surface, right? So therefore, here I hope you can understand that. Yeah, here I have written it's an infinite cylinder. It's a this, and this, and the coordinate lines, intersection and all we will discuss. So rho can extend from 0 to infinity. This I already discussed. Now, what are transformation relations? The transformation relations you can write like this. Here, x, y, and z are the 3D coordinate system. X, you can write it as, for if you look at this picture, there is a rho here, there is a phi here. X will be rho cos phi, isn't it? If you look at this picture around this here, if you know your trigonometry, y can be written as rho sine phi, and z is z. This is transformation relation from this thing, rho phi z coordinate to x. Now you can write the reverse transformation. If you take the square of this thing, x squared plus y squared, and if you add this two, this will be rho square into square root of sine square, cosine square, that will be 1. So you can obtain this rho equal to square root of x squared plus y squared. If you take this ratio, then you get tan phi equal to y upon x. So phi will be tan inverse of x, and z is z. So this is the reverse transformation relation. Okay, so if you remember, earlier I have written one transformation relation as x as a function of u1, u2, u3. So here in place we write x as a function of rho, phi, and z. So what is that over here? X is equal to rho cos phi, right? And the reverse here is that when you write u1 is equal to u1 as a function of x, y, and z. Here in this case, we are now having we are now having u in place of u1. We now have rho as a function of x, y, and z. So here you see that rho can be written as square root of x squared plus y squared. So that's what we mean by a reverse transformation relation. Okay. So the coordinate variables in cylindrical systems are rho, phi, and z, and the coordinate surface and the coordinate lines. One of the coordinate lines is a curve, it's a circle. One of the coordinate surface is also a curved surface, which is an infinite cylinder. So I think I will stop here. Otherwise, if I feed you too much information at the same time, it might not be productive. So let's stop here. So I think we can, based on this introduction of this cylindrical coordinate system, we can continue our next lecture. Please go through the material I gave you. Everything is there in my notes also. Okay, so I will stop now. If you have type your attendance, you can exit the meeting.